All right, so starting with movement on the celestial sphere. Um, I asked this question in the activity. Imagine you are alive 400 years ago and you regularly looked up into the sky at night. How do you think you could detect planets in the sky? And based on your experience working with Stellarium in the activity last time, I got lots of great responses from you. You said the planets move much faster than the stars, right? If as time goes on, the planets move through the sky more quickly than the stars do. They're also generally brighter because they're closer to us, and they are reflecting light from our sun, and they can be differently colored than the stars. So that's great observations. Another great observation, planets move on a different pathway than the rest of the stars, right? They take a different track in the sky and they move more quickly. And then also insightful, sometimes planets, unlike stars, seem to stop moving and reverse their direction. So that's what we're calling retrograde motion. And this is a great segue tying what we looked at last time in Stellarium to the topics of today. So thanks for these great observations. I want to talk about this different pathway a little bit more. So if we look at our celestial sphere, that's of course this imaginary sphere that surrounds the Earth. It's not real, but it's a useful construct to help us understand the motion of items in the sky. We say that stars are sort of fixed on that celestial sphere. And so as we turn, right, as the Earth rotates, then it appears that the celestial sphere is rotating around us. So the stars seem to circle around the celestial poles, but the planets and the sun and moon don't travel at the same rate, and they don't follow in circles around the celestial pole in the same way. So instead, they seem to move, as you said, faster than the stars and on a different path. And both of these items together, this is why the ancient astronomers called the planets wanderers, because they seem to wander around in the sky more freely than the stars. So the sun moves across the surface of the celestial sphere also, right? It's not just the planets, but the sun and moon also move across the celestial sphere. And it makes one complete path once per year. And we call this path the ecliptic. So if we're going to draw the ecliptic on the celestial sphere, it would be tilted from the celestial equator. And this isn't because the sun travels on that tilted path, right? Because this is an artificial construct. Instead, it's that the Earth is tilted in its orbit around the sun. And that makes the ecliptic appear angled from our perspective. So let me see if I can show you a little bit about, what that means. So, okay, here we go. So if we look at the Earth in a frame of reference that's not tilted with respect to the sun, so if this red line is in the plane of our orbit around the sun, then the Earth is tilted by 23.5 degrees with respect to its orbit. And therefore, the ecliptic appears angled relative to the celestial equator by the same amount, 23.5 degrees, our axial tilt. All right, so from the perspective of the sun, the Earth is the one that's tilted. But from the perspective of observers on Earth, it appears that we are not tilted and that the sun is tilted on the ecliptic. All right, hopefully that makes sense. So this is it's a frame of reference that leads to this ecliptic appearing tilted. Okay, and the ecliptic is really important. It's not just the sun that moves across the ecliptic. My slides are being really slow to advance again today. The moon also follows the ecliptic. And so as we watch the moon's path over the course of many nights, it also traces out that same path across the sky. So a question about lunar motion: how long would it take the moon to make one complete trip around the celestial sphere? So let me open up that poll. And I'm seeing the vast majority of votes for option number 3, that it takes 1 month to move across the celestial sphere. And of course, this is, why we even divide our year into months, because this is sort of a natural time scale that's set by cycles in the sky. So the natural time scale of the Earth in motion around the sun gives us the year. The natural cycle of the moon around the Earth gives us the month. Maybe if the moon had a different orbital period around the Earth, we might have different calendar. So this is kind of one of the connections between astronomy and society, right? Is that what we observe in the sky actually does impact our day-to-day life. Okay, I think I have one more question here. Yeah. So sometimes, right, during a solar eclipse, it looks like the moon is blocking out the sun, right? There was a solar eclipse in August of 2017 that was also part of the activity. And so what is true about the moon and the sun during that solar eclipse? So let me restart that poll. Okay. Okay. So remember declination and right ascension. Declination is the angle from the celestial equator up toward the north celestial pole or down toward the south celestial pole. And right ascension is kind of the, angle around the, azimuthal direction, I guess, of the sphere. So I can't remember where the 0 point for declination is, and I didn't look it up, or sorry, right ascension. Okay, so declination is sort of the same as latitude, and right ascension is sort of the same as longitude in terms of how they're measured on the sphere. And so during a solar eclipse, if the moon and sun are lined up so that the moon appears to block the sun, then they have to have both the same declination and the same right ascension. So their position on the celestial sphere is exactly the same at that moment. We'll talk about eclipses more when we talk about the moon, but here's how it relates to this particular topic. All right. What questions do you have left about declination and right ascension and the celestial sphere? Okay, so I mentioned also the planets move across the celestial sphere. So the sun and the moon travel along the ecliptic, which is tilted from our celestial equator, and also the planets travel close to the ecliptic as well. So this is a screenshot I took from this rotating sky globe tool that I found. It's similar to the one I mentioned last time, but it's actually online, so it's easy to use. You don't have to download any app. So if you go to this link, then you can look at this model of the sky. You can turn on these lines for right ascension and declination. You can change your location, you can change the time, and then you can plot the ecliptic. So the ecliptic here is traced out on this yellow line. And I've also got the planets as these little pink points. And so over the course of the year, the planets travel along the ecliptic. Here's the rotating sky map. Okay. So you can change your date, you can change your location over here, and then you can turn on and off different features like the ecliptic. I think that's here. All right, so there's the ecliptic. You can take off and on this right ascension and declination grid. But I think it's nice because if the ecliptic were lined up with the celestial equator, then it would be lining up with one of these gray lines of declination, right? But it doesn't. So this is a nice illustration of how the ecliptic is tilted. Okay, so I can, drag the date along here and watch the planets and the moon travel along the ecliptic. So you can play with this if you want to get more of a feel for those motions. But this is like a model, right? This isn't really what it looks like in our sky. So that's what I wanted to show you in Stellarium is what does this look like in our sky? So this is kind of the same view that we were looking at in the activity last time. And if I come here and hold down my date, right, then I can watch the planets move along. There goes the moon. There goes the moon again. right? So I can start to get a sense for where the ecliptic is because I can see the moon traveling along this path, right? So now if we watch Venus, Mars, Mercury, Jupiter, as I continue to drag the date along here, then I can see them also following along that ecliptic. So this is, if I was going to observe at the same time every night and plot out the positions of the planets, then this is what the end result would look like. And this is exactly what astronomers were doing to come up with the models of how planets move. Now we just saw something really interesting. So let me back up in time again. All right, so now I'm going backwards. Okay, so here, right, watch what happens to Mercury in the middle of the screen. As I go forward in time here, it's appearing to move backwards right now on the sky compared to all of the other planets in the sun. And now it's going to turn around and move forwards again. So this is what we refer to as retrograde motion, right? It's the illusion that we have that sometimes planets appear to stop, turn around, and then turn around again and continue in their forward motion. So this was, probably really confusing to people and why the planets were called the wanderers. So this is something that any of our model of the solar system has to be able to explain.